Similar with Carbon's method, Aashta provides empirical formulas in the distribution of shears and moments across the girders of the bridge. Check it out here in Bridge Engineering. When trucks pass through a bridge, they impose live load. Although they follow a lane, the girders would not necessarily carry equal loads, and not all of the truck load will be carried by a single girder. Moreover, take a scenario when trucks are driving side by side each other. Aashta provides the distribution factor to identify the percentage of truck's weight an individual girder must carry. The distribution factor differs from moments and shears. It also differs according to the girder. Let's start with the interior girders. The two scenarios to also consider are when the lanes are loaded or just one truck passing. When multiple trucks are passing by the critical portion of the bridge, we take the distribution factor as shown. On the other hand, if there is only one truck passing the midspan, we have the following DF. Both equations have the same parameters, where S is the spacing of girders, L is the span of the girder or the bridge, T is the slab thickness, and K sub G is the longitudinal stiffness parameter given in mm raised to 4. The constants from the equations consider the conversion factors and the multiple presence factor. However, if we want to know what these quantities are, the first term covers the spacing, while the second term covers the span, and the third term is for the bridge's stiffness. Let's also analyze the two categories. Two or more lanes loaded is considered the worst-case scenario, or when the bridge is full of traffic. With the presence of multiple trucks in the bridge, the interior girders would be assumed to reach their maximum stresses. For one design lane loaded, there is the presence of one truck, where the weight is concentrated on one side of the bridge. The distribution factor on the exterior girders depend on the interior girders DF. For two or more lanes loaded, the DF needs an adjustment factor, where this adjustment is computed as 0.77 plus D sub E over 2800. D sub E is the distance from the center line of the exterior girder to the inside face of the curb or barrier. For one design lane loaded, we employ the lever rule, which we have already used in the determination of the reactions in the loading analysis. The distribution factor is the product of the reaction and 1.2, where the constant is the multiple presence factor for a single lane. So to compute for the final moment, multiply the distribution factor with the computed girder moment, where this moment considers the higher value between the moment from the design truck or design tandem, multiplied by the impact factor, then the moment from the design lane. Note that in contrast with the computation of moment done in the preliminary load analysis, we don't consider MPF in the computation anywhere, as the empirical formula has it covered. From both DF of moments, there is the stiffness term which uses K sub G, or the longitudinal stiffness parameter. This is computed with the equation shown, where A is the cross-sectional area of the girder, I is the moment of inertia, which shows BH cubed over 12 if the girder is rectangular. N is the modular ratio taken as the ratio of the modulus of elasticity of the girder versus the deck. Remember that E for steel is 200,000 MPa, and that of concrete can be computed from 4,700 times the root of F prime C. If ever the deck and the girder have the same material with the same strength, then the ratio is taken as 1. The last parameter from the equation is E, which is the lever arm, or the vertical distance between the center of the girder and the center of the slab. This then includes the girder depth, the slab depth, and the hunch. How about the distribution factor for shear? Similar with moments, this will be taken with the location of girders. For interior girders, again having the same loading scenarios, the equation for 2 or more lanes loaded is as shown. And for one design lane loaded, we take dF as 0.36 plus S upon 7600, where S is the girder spacing in millimeters. Shear does not consider stiffness, making the equations much simpler than those for moments. Again, exterior girders depend on the interior girder's dF. For 2 or more lanes loaded, the dF turns as the adjustment factor times the interior girder dF, where the adjustment factor is taken as 0.6 plus d sub e upon 3000. D sub e is still the distance between the exterior girder and the inside face of the curb. For one design lane loaded, we still follow the lever rule to take the reaction. The shear calculation V final is the shear computed for the girder multiplied by the distribution factor. Similarly, the shear of the girder depends on the higher shear value between the design truck and the design tandem, which is then multiplied by the impact factor. Then add the shear brought about by the design lane. The multiple presence factor is also integrated in the dF equations, thus no need to place it here.